All right. Hello, everyone. How's it going?
Good.
Good. Thank you. All right. Well, happy Monday to everybody. The plan for today is to kind of wrap up the material on worksheet 18 that we were talking about last time, equivalence relations. And then we can chat about the exam. We can chat a little bit about the material that we'll pick up with after the exam as well. So just so you guys know, the exam Monday, today's Monday, the exam Wednesday is on worksheets 11 through 18 that we've covered since the last exam. So that's going to be induction and cross products, Cartesian products of sets, and relations and equivalence relations will be that material, and the format of the exam, how it's going to be administered, will be the same as last time. So there'll be a multiple choice part and a written part, same as exam one. So maybe I'll just say, if you have any questions about the exam, just hold off on that for a moment while we kind of wrap up some of this material from last time, and then I'm happy to answer whatever questions you guys might have. Okay, so I want to just start actually with a couple of comments about the homework. So I did grade your last homework assignment, homework 7, and posted my comments on your assignments as well as the solutions. Let me try and track this down. Let's see. Yeah, and so here, I think there is a bit of a delay. Here we go. So here are the solutions for homework 7. And I want to kind of just get into maybe something like question 2, where you had this recursive relationship that was defined. You were asked to conjecture if there is a more explicit formula for this sequence and then prove that it works. And so these look pretty good. The explicit formula I think everybody got was 2 to the n minus 1 over here. And the thing that I want you guys to watch out for is the base case over here. So here's an example of an incomplete base case. This is mine. I did this on purpose here. So this recursive sequence is defined differently for the first term and the second term as it is for the general terms, right? So B1 is defined a certain way, B2 is defined as 2, and then all the other terms are defined like this. So if you do a base case and you check the case for n equals 1, great, that checks out. Then you go on to do your induction step. And now what you want to do is you want to show that b to the n, and we'll set that equal to k plus 1, is equal to 2 to the n minus 1. And so that induction step requires us to use induction on b to the k and on b to the k minus 1. Right? So we need the 2 previous cases in order to prove the nth case. So in order to prove the k plus 1 case, I need the kth case and the k minus 1 case. So if you were going to try and do this for B3, which would be something like this, unless you've proven the case n equals 2, I can't use induction on this one, right? In the base case, we've only proven it for case 1, so I certainly can replace B1 with 2 to the 0 with power, but I can't do anything with this because we haven't proven anything for the second case. So when you're doing these base cases, be sure that you're proving the right number of base cases. Sometimes people are proving more than they need, which is also which is less wrong, but it's just a little bit less elegant if you're just writing out tons and tons of cases. So try and think as you're getting ready for the exam, how many base cases would I need to prove? When you're working with recursively defined sequences like this, it's always going to be, I need to prove as many base cases as like special cases of the terms in the sequence And then once I hit the general term, we're good to go. So in a problem like this one, since the first and the second terms in the sequence were not defined recursively, they were just given to us, we would need to check both of those two cases before going on to the induction step. So I'll just say, like, generally speaking, your homework assignments look really good. You guys are doing an awesome job with induction. It's maybe just a little bit here, a little bit there. And I will say the most common thing on this assignment was not knowing how many base cases to prove, which makes sense. This was the first assignment where we really had to think about that. So I think that for some of you, you're not quite there yet. Still put some work in that process. But any questions about that last homework assignment, or what I'm kind of referring to here? Okay. Yeah, so just keep an eye on that. Other than that, no kind of general across the board comments on that homework assignment. Okay, so last time we were working with equivalence relations, and we were doing some of these proofs. So remember, an equivalence relation is a relation which satisfies three properties: reflexive, symmetric, and transitive. So last time, let's see where we were. So we proved the parity relationship. We did the mod relationship. And we talked about the perpendicular lines not being a relation. And I think maybe we started in the breakout rooms with this one, now that I'm remembering back to Wednesday, but we didn't really get too far into this one. But you guys did talk about it a little bit. Okay, I don't think we started this anywhere. So let me pick this up and come to a fresh page. Okay, so when you're thinking about these relations, I think if you're getting stuck about what to do, it might be good just to think about a couple of cases just to make sure you understand what this relationship is, how it's defined. So we have this set of the first 100 natural numbers, 1 to 100, and we're going to define this relation S on the power set of X. So now our elements are going to be subsets of X, right? Since that's what the power set is. Okay, so just to say, okay, let's say we have these three sets here. First of all, these are all elements of the power set of X because they're all subsets of X. And so this relation X is the smallest element of each. So I would look at A, I would look at B and say, okay, the smallest element of A is 2, the smallest element of B is 2, those are equal to each other. So here we would say that A is related to B. Okay, whereas C is not related to B since they have different smallest elements. So that's what this map is doing. Any questions about how we define that? Whoops. Okay, so let me just zoom that down. So there's just some scratch work. So this is an equivalence relation. So in order to prove this is an equivalence relation, we've got three properties that we need to prove. right? The reflexive, which is a for all statement. Okay, so in order to prove reflexive, right, we would say for any element in our set, and in this case, the power set of X is the set related to itself. So here, to start these proofs, we would say, let A be an arbitrary element in the power set of X. So now we'll let A denote the smallest integer in set A. And then since the smallest element of A and I actually, I don't think I needed this over here. So I certainly could just go back and delete that line out of my proof. I don't think it really helps anything here. It might help in some of the others. So really with the reflexive property here, just want to make sure that we're understanding what it means for an element to be related to itself and checking that. Okay, any questions? Okay, then would come the symmetric property. And so for the symmetric property, what we're trying to show is if A is related to B, does that imply that B is related to A? Let's see, sorry, you've got a slight delay here. I'm just going to plug this in. Maybe that will make the connection faster. Prompted. Got it. Let's see. This is that does not seem to be working. I don't think you guys could see anything, right?
No, it's just a blank screen.
That's not very exciting. Okay, let's try this again. Sorry. Okay, here we were. Sorry about that. Okay, you guys can see that. Yeah, just let me know if there's some sort of a lag or something like that. I think there was before. Okay, so we got the reflexive property. And now we're trying to prove the symmetric property, right? Which would be if A is related to B, then B should be related to A. And we've saw plenty of examples where that doesn't hold, like less than or equal to sorts of properties. So now, since this is an implication, we can prove this directly. Is typically the way this might go. So let's suppose that A and B are elements of the power set of X. Okay, so notice I say that sets A and B are elements of the power set of X, which is the same thing as saying they're subsets of X. So you could say that either way. And we're going to suppose that A is related to B. So now it might be nice to just say, well, let the smallest integer in set A and then let's let the smallest integer in set B be denoted with a b, lowercase b. And since those two are related to each other, then we know that their smallest elements are equal to each other. I think, again, I didn't necessarily need to even give these smallest integers denote them with any special notation, but all we're saying here is that the smallest element of A equals the smallest element of B. Therefore, the smallest element of B equals the smallest element, which is an integer, in A. So that tells us that B is related to A. Any questions? Okay, and then we've got one more property, right, which is the transitive property, which is also an implication which says if A is related to B and B is related to C, then A should be related to C. Okay, we've got three sets. We're going to assume A is related to B and that B is related to C. So this means that the smallest element in A is equal to the smallest element in B. Okay, and we also know that the smallest element in B equals the smallest element in C. Okay, so basically here we're just using the transitive property of equals, right? So we've got the smallest element in A, therefore must equal the smallest element B. And that would prove that last one. And I left out a word here. Need smallest integer in A equals the smallest integer in C. Any questions? So you've got a couple of questions on your homework, right? That ask you, thanks Giselle for thumbs up, good to know, that ask you to prove a certain relation is an equivalence relation, and then say something about the equivalence classes. So I just want to be sure that you got the memo about us doing equivalence classes afterwards. So I did update that homework assignment. Hopefully you're looking at it to say, don't need to worry about equivalence classes here and here. And I realize there's another place that you can strike out the equivalence relation. So in question 3, you just need to prove that that's an equivalence relation. Don't worry about the equivalence classes of that. Okay, so let's see. Okay, so let's try a couple of others, 6 and 7, which are also working with power sets. So 6 is using the same x as 5 was using. And 7 is now thinking about subsets of all the integers, so the infinite number of things. So let's think about these relations here. And the question is prove or disprove whether this is an equivalence relation. So in 6, this T relation is saying that we're going to take the smallest element of A if it's less than or equal to the smallest element of B. So just to do some scratch work over here, okay. Well, I realized that you're not looking at my iPad now. Sorry. Thank you, Ken. And Zoe, yes. Let me take you back to my iPad. Okay, so sorry. We're working with question 6. Question 6 is using the same set X that we had in the previous problem. So we're thinking about elements here are subsets of X. And now this relation is the smallest element is less than or equal to the smallest element of B. So let's just kind of go through some of these, just looking at one case. And maybe this will give us an indication of what's going to work or not work. So the question here is A related to itself. So I'm going to launch a poll here. This says, is it one-to-one? You can disregard that. My question is this set A related to itself through this relation T? Okay, take another couple seconds if you're still thinking. Okay, so here are the results from that. And so this is related to itself. And the key here, right, is the or equal to. So if this was like strictly less than, then no, it would fail the reflexive property. So it seems like because we have that equal to, the reflexive property seems like it should be okay. This is by no means a proof of the reflexive property, right? We're just doing an informal check. So next would be if A, let me put it like this, is related to C, so we're going to take these two over here. So the question I'll ask again is, again, you can ignore this one-to-oneness. The question here is, let's consider the two sets here, A and C. A is related to C because its smallest element is less than or equal to the smallest element of C. The question is, what about the symmetric property? Is it going to therefore be true that C is related to A? So tell me what you think about reflexive property of this relation. Okay, take another 10 seconds, please, to get your answer in. The question here is nothing about one-to-one. Is this relation T reflexive? That's what we're thinking about. Or excuse me, symmetric. That's what we're thinking about. We did the reflexive part. All right, great. So that seems pretty overwhelmingly to be no, and that is correct. So here, basically, right, we've talked about the less than or equal to relation and the equal relation already. So question 5 was an equivalence relation because the equality relation is an equivalence relation. In question 6, we have a problem because this relation of less than or equal to is not an equivalence relation. So we've got that this is true in this case because 2 is less than or equal to 15, but 15 is not less than or equal to 2, so C is not related to A. So let's kind of prove this more carefully. So number 6 here, we're going to claim and so to prove that, we just need to show that one of these three properties doesn't work. So I don't even need to go on and think about the transitive property, though that is whether or not that holds or not, because we need all three of them in order for it to be an equivalence relation. So if we can show that any one of them doesn't work, that's enough. So we're going to disprove this with a counterexample. And we pick any counterexample that you can imagine. Here's a simpler one where we have A is related to B but B is not related to A. So T is not reflexive, or excuse me, symmetric. And that's all we need to do for disproof. Okay, any questions of that? I think I will stop at this point. There are a couple of others that we haven't got onto. We didn't do 7 or 8 or 9. I'll put up those solutions. You can think about them as like practice problems for the exam. So these would be good to go over as we're getting ready for the exam. I think at some point, you know, me going through them for you maybe might not be as helpful as trying to just go through them on your own. But any questions about relations, these properties of relations, or anything else? Okay, so then let's talk about the exam. And I'll give you guys a chance to ask any questions. And then I do want to start a little bit on the material that we're going to be talking about after the exam. I am going to put up a quiz for Monday, just so you guys are aware. You've got the exam on Wednesday. There'll be a quiz on next Monday. It'll be on kind of what we talk about now, or at least after you ask some questions about the exam. It'll kind of be about an introduction into equivalence classes. So you won't have anything in addition to watch for the quiz on Monday, but kind of reviewing what we talk about today should be enough to get you ready for that quiz. So yeah, so for the exam, let me just come to a fresh page. Same idea. We've got part 1, which is going to be multiple choice. And then we've got a part 2, which is written. So let me just say, you certainly should be prepared to do an induction proof or proofs. You should also be prepared to prove something is or isn't a relation, what we've just been talking about now. Okay, and so kind of related to that would be properties of relations. And maybe kind of before we talked about relations, we talked about the Cartesian product. Which meant that we did some proof with sets, like prove this thing is a subset of that or equal to that or so on. So kind of the main proof techniques here are going to be induction. How does induction work? How to prove something is an equivalence relation. So the definitions of reflexive, symmetric, transitive, and then doing some proofs with sets. So in particular, Cartesian products of sets. So if you're kind of breaking it down, I would say, you know, these two are going to be, as far as the written part goes, I don't know, maybe like 40% of it will be induction, 40% of it will be, roughly speaking, and I don't know, it'll, what I'm trying to say here, these are not accurate, but I'll say a little bit less with Cartesian products, a little bit more with induction and relations. Maybe not quite that drastically, but that's the idea. Anyway, study all of it. Don't ignore any of it. Any questions about material for that exam or questions about the exam itself?
Is homework 8 pretty good practice for what to expect on the exam?
Well, so homework 8 had questions kind of relating to the last two parts here. I would say this and this. There are some proofs with sets, and there are some stuff with relations. There's no real induction on this assignment. So I would say that this is the only homework assignment that you've had on these parts over here. So yeah, that would be good practice for those types of questions. But the previous two homework assignments were on induction. So you definitely want to look over those as well.
Okay, thank you.
Yeah, and so yeah, I think that this homework is good. The homework that you're working on for tonight, that's certainly good practice. There's some, we don't do all of the problems on all of the worksheets. We get through a lot of them, but sometimes I leave some for practice for you guys. And so those would be good to go back over to practice. And there are also additional practice problems that I suggest from the textbook. So I think as you're getting ready for the exam, I would say it would be good to just have like a general understanding of these definitions and these proof techniques, have that down, and then gauge yourself, practice that understanding by doing different problems, by doing different proofs. And kind of some nice problems that are good to practice that I think really get at some of the subtleties of these relations. When we first talked about these properties of relations, we said, okay, let's consider a set A, and then let's find the relation which is reflexive and transitive, but not symmetric, right? And so we thought about ways that we can find relations that satisfy some of these properties, but not the others. So those would be good to practice. I'm trying to remember when we did that, maybe 1 or 2 worksheets ago. Yeah, so this was worksheet 17. So worksheet 17 was the main worksheet when we talked about the properties of the relations. And then worksheet 18 was really nothing new, right? It's just how do we prove that something satisfies all of them or doesn't satisfy all of them. What else? Other questions?
Yeah, so for the induction part, like what problems do you recommend that we study?
For the induction part, I missed the tail end of that, Diane. Which?
Yeah, like what problems do you recommend that we study like for the induction part?
So those would be like whatever the worksheet numbers were. So I think that was like worksheet 12 and 13, 14 were all ones where we did induction and the homework assignments related to that, and the additional practice problems related to that too. So I think between the worksheets and the homework and the additional practice problems, you've got a lot of proofs to try and go back over, review, or I think there's a balance between reviewing something that you've already proven, which you might be recalling from memory, and as well, you want to also be trying to prove things that you haven't done already, just to see, how can I, on the exam, you're going to have to prove things that you haven't already proven. So that's a good way to just test yourself before the exam.
Oh, okay, thank you.
So there was a question that came into me about, is there any material from the first part of the semester that was on exam 1, which was like direct proof, contrapositive, contradiction, that the focus of this exam is on induction and relations. I'll just say, like, when you're proving something is a relation, we're doing direct proof for implication. So in that sense, yeah, we don't want to forget direct proof. I don't think there's anything that you're going to have to do with contradiction or contrapositive. I'm not going to ask you multiple choice questions on them. But, you know, hey, sometimes those are useful proof techniques. So I would say don't forget about them. We're going to use them again after this exam. So yeah, I would say getting the general idea behind them might be useful, just because that might be a useful proof technique. When we've been doing relations, we haven't had to do anything by contrapositive or contradiction. Direct proof has been working for us. That doesn't mean it's always going to work, but that seems to be working fine. Okay, any other questions? Okay, so let me open up this worksheet 19 and I can chat it into everybody if you'd like. Actually, I don't know if I took this down off of Canvas, but let me post it here anyway. Okay, so this would be like section 11.4, where chapter 11 deals with relations. So I want to kind of first just start with page 2 of this document, which defines a partition of a set. And so for anyone that maybe is taking a probability course or something else, you might have seen these partitions in other classes. So a partition of a set. So we have a set S, and P is a partition. It's going to be a set of subsets. That's what we're going to call the partition. And in order for P to be a partition, there are going to be a couple of properties that need to be satisfied. So one is each of the subsets is pairwise disjoint. So basically, this partition is going to be made up of a bunch of sets. I'm just going to call them A1 up to AN. So each of those sets AI is a subset of S. That's kind of the first thing. And this is going to have this property to say pairwise disjoint means if I take any two subsets that are any two distinct subsets in this partition, their intersection is the empty set. So we've got kind of one property over here. That's the pairwise disjoint. Okay, we need them to be non-empty. So that means each of these sets in the partition, right, needs to contain something. Is not the empty set. And kind of the last one is the union of all of these sets should give us back S. So just to kind of clarify this, okay, so first of all, each of these things is a subset of S. Secondly, each of these is non-empty. Secondly, each of them should not be the empty set. Another condition is their intersection of two distinct subsets in the partition should not contain the same element, so they should be empty. And the fourth one is if I take A1 union A2 union A3 all the way up to the nth one, we should get back the set S that we started with. So really there's three conditions, I'll say. Like number one, it's not something we necessarily need to check. That's usually pretty quick to see if we've got it. So kind of the short story here is for P to be a partition, each element in our original set S should appear exactly once in one of the sets. In the partition. So therefore, if it only occurs in one of those sets, that's going to ensure that the intersection of any two sets is empty. And we want to make sure that each element appears in exactly one of the sets so that when we take the union back together, we get S. Okay, any questions about that definition? Okay, so I'm gonna open up, sorry, I never hit that button before. That was interesting. Okay, sorry, I'm gonna open up this poll again that says, is it one-to-one? But what I'm asking here is this first example in part A, is this a partition? So yes or no. So yes would mean that it is a partition. No would mean that it's not a partition. Okay, great. Thanks for the replies. So everybody says yes, this is, and yes, this is, right? So here what we want to make sure is we've got our set S over here is first 6 integers, or first 6 natural numbers, I should say. And so what I can see is all of, when I take the union of 1, 3, and 2, and 4, 5, 6, we get S back. So that checks out. We can check that none of these sets in the partition share any elements in common. So this intersect with that would be empty set, this intersected with that would be the empty set, and so on. So they are disjoint. And none of the sets are empty, right? So that satisfies all of those conditions. They're all subsets of the original set. So that's a yes. Good. Any questions? Okay, what about B? That form of partition. Okay, so here we're feedback there. So people were saying that one looks pretty good. That's right. So I'm just kind of writing out what this partition would look like. So that would be all the even numbers. Of grouped with all of the odd numbers, and a second set with all the odd numbers. And so these are disjoint, right? A number can't be even and odd at the same time. And all of the integers have to be either even or odd. There's no third choice. So when we take the union of these, we'll get all of the integers back. Okay, let's take a look at one more example of this. Let's try to see. Whoops. Let me relaunch it. So you think this is a partition of the integers, or excuse me, of the natural numbers or not? So here we've got primes, we've got composites, and we want to know, can we partition the natural numbers into primes and composites? Okay, so here were the results, though someone chatted in, they wanted to change their vote from a no to a yes. So either way, things are pretty divided here. So this is actually not a partition. And the reason why might be getting into the nitty-gritty of what it means to be prime versus composite. So for someone that said no, definitely, or maybe I'm not certain, why would this not form a partition of the natural numbers?
Because 1 isn't prime
Good, that's right. So the number 1
or composite.
is not prime or it's not composite, right? It's kind of a special number when it comes to that. So if we want to partition the natural numbers, we would need to put 1 in here and then the primes and then the composites. So 1 is not prime and it's not composite. So a number is prime if its only divisors are the number, it's kind of defined as P is prime if P is not 1 and its only divisors are 1 and itself. So it's more of a bookkeeping thing in mathematics. You could ask, why did we decide not to make 1 a prime number? I don't know, just the way it was done. Okay, any questions about that? Okay, so that's the notion of what a partition is. So part of this quiz that you guys are going to have to do on Monday after the exam is going to ask you about the definition of a partition. Is this thing a partition? This sort of stuff. Okay, so now let's relate this back, this notion of partition, back to equivalence classes. So we say an equivalence class of A is going to be the set of all numbers or all elements that are related to A. Yeah, so for example, the one that we just did, question 5 on worksheet 18, was asking us about the smallest element relation. Where X was the set of the first 100 integers, natural numbers. And we said this was an equivalence relation, and then you can think about the equivalence class 1 would be equal to the set of all elements such that X, in this case A, is related to 1. So in other words, it would be all subsets of X be all subsets of X that have 1 in it, the number 1 in it. Since if 1 is in it, it has to be the smallest one. So these equivalence classes is a set itself. Okay. Let me just say, we'll see that there are different ways that we might denote an equivalence class. We're going to say that A is the representative of this class because it's the element that we're using to describe the class, right? We're saying that this is the set of all things that are related to A. And so if we think about this smallest element relation, right? These two equivalence classes, what this theorem is saying is because this smallest element relation is an equivalence relation, the corresponding equivalence classes should be the same no matter which element I pick from that equivalence class. So the set of all things that are related to 1, the set 1 should be equal to the equivalence class, which would be the set of all things that are related to 1, 2, since these guys have the same smallest element. So what this theorem is saying in 2 is that equivalence classes are super nice. This is not true for any relation, but if your relation satisfies these 3 properties, reflexive, symmetric, transitive, then it is going to be true that if 2 things are related to each other, then their equivalence classes are going to be equal to each other. So in other words, it doesn't matter what representative we pick to express the equivalence class. This is not true for relations that are not equivalence relations. Okay, so here, a couple of things to note is this is an if and only if statement. So this is a biconditional statement. So there's 2 things that you would need to show, and that is if equivalence A is equal to equivalence B, that's going to imply that A is related to B. And then we would need to show the other direction, which is if A is related to B, then then their equivalence classes are equal. But the short story here equivalence relations give us nice, well-defined equivalence classes. So in other words, it doesn't matter which element from the equivalence class we use as the representative. So maybe rather than prove this theorem, which we'll get to, let's just do an example together. And not worry about all of these proofs here. Yeah, maybe we'll take one from your homework assignment that I removed. So let's consider the following relation. So this is on your homework assignment that you're working on for today, number 3, which first asks, we're going to let R be this relation which we're going to define on the set of integers as follows. We're going to say that A is related to B if and only if A plus B is even. So on your homework, you prove that this is an equivalence relation that it satisfies those three properties. Let's take that for granted. And now the second part is what are the equivalence classes? So let's just kind of think about what one of them might look like. So if we take the integer 0, this would be the set of all integers such that integer k is related to 0. So what would be some elements in this relation, in this equivalence class, I should say? Can someone tell me what's another integer that would be related to 0 by this relation? Let me just replace k related to 0 with what that means. What's an integer that when I add it to 0, awesome, 2, oh, thank you, I saw 1, 2, 4, 6, 8. And here we have integers, so we have negative numbers too, right? So if I'm listing this out, be the set of all the even integers. And because this relation is reflexive and transitive and symmetric, right, we could think about, well, what would the equivalence class of 2 look like? Well, it would be all of the things, all of the integers, such that when I take it and add it to 2, we get something even. Okay, so that's what we mean by saying equivalence class of A is equal to equivalence class of B. So in other words, it doesn't matter which thing in this set I choose to be its representative, they're all going to be the same. So the equivalence class for 2 equals the equivalence class for 0, right, equals the equivalence class for 100, equals the equivalence class for any other even integer. So this equivalence relation, two integers are related if their sum is even, divides the integers up into two equivalence classes, right? One of them, all of the even integers, one of them, all of the odd integers. Which are the even and the odd integers. which we already checked when we were talking about partitions, that this is a partition of the integers. So kind of one result that we'll prove next time is the equivalence classes that I can now represent in terms of their equivalence classes. So this forms a partition. Since this is all of the even integers, this equivalence class is all of the odd integers. Okay, so I'll stop here, and we'll pick up from this point after the exam. Anything that we talked about with equivalence classes or partitions, you guys won't be asked about that on the exam on Wednesday, but we'll pick up at that after the exam. I wasn't planning on I'll open the quiz after your exam, so let's not worry about this. Focus on getting ready for the exam on Wednesday. After the exam, I'll open up a quiz that's just going to ask you about some definitions that we just talked about. And I'll just post an announcement to you all just so that you remember to take the quiz over next weekend, so that when we come back on Monday, we'll have this stuff fresh in our minds and we'll be able to hit the ground going. Okay, well, if you guys have any questions about the homework or getting ready for the exam, Lindsay has office hours today, right? And I've got them tomorrow. So Lindsay, when are your office hours for today?
Today they're from 1 to 2, and then I also have them on Wednesday before the exam from 9 to 10.
Okay, and I've got mine tomorrow from 1:30 to 2:30. Yeah, that's mine tomorrow. So yeah, so you're welcome to stop by our office hours. Yeah, good luck getting ready for the exam otherwise, and I will see you guys on Wednesday. If you can get into Zoom a little bit earlier, maybe 5 minutes early on Wednesday, we can just go over the instructions and make sure that we get the exam started on time. Yeah, otherwise, good luck getting ready, and see you guys on Wednesday.